Hello, everybody. My name is Ali Reza Haddadi, and I'm going to talk about large-scale graph processing on commodity systems, understanding and mitigating the impact of swapping. This work has been done together with David Blackshaffer and Changkyun Park. So we're going to introduce the problem now. The problem is that in the graph processing applications, graphs are often huge in size, and we only have a limited DRAM capacity. So the graph workloads do not fit into the main memory. We have two possible solutions for that. One is non-commodity approaches, which require algorithmic and hardware modifications. They are costly and not flexible. We have a well-known commodity approach, which is virtual memory and swapping, but it's known to be slow. So in this work, we are going to see how slow it is and what are the system and storage behavior and that it slows it down. And from there, we are going to optimize. So in this work, we are doing a performance characterization and optimization of swapping for graph processing applications. Now let's see how slow is swapping. In this work, we have used Gap Benchmark Suite, which has 6 different algorithms and 5 different input graphs. And I should note that swapping only occurs when the workload does not fit into the main memory. Let's take BFS application as an example. So in this graph, we are going to see the amount of slowdown we get if a percentage of the workload does not fit into the main memory. For example, for BFS application and cron input graph, if 70% of the cron input graph does not fit into the main memory, we should get a slowdown more than 16x. Well, the amount of slowdown varies for different input graphs, and it also varies for different applications. So swapping significantly slows down the system, and the slowdown varies depending on the benchmark. Now let's have a deeper look at this point, where 70% of the workload for BFS algorithm and web input graph does not fit into the main memory. And let's see where the slowdown comes from. So we have a case study here. BFS algorithm input, the web input graph, where 70% of the workload does not fit into the main memory. Out of the entire execution time, only 7.4% is dedicated to the user program, which is BFS algorithm. And 4% of the execution time is dedicated to the operating system when it handles the system call. 6.7% is dedicated to a part of the operating system where it prepares for swapping. And for 80% of the time, the CPUs are doing nothing but idling and waiting for the SSD. And for 1.8% of the time, the operating system handles the interrupts coming from the SSD. So swapping overhead consists of page fault handling slices, which contribute to 8.5% of the execution time, and a giant idle slice, which contributes to 80% of the time. We can categorize these slices into 2 categories, where CPU works and where CPU idles and SSD works. So in the page fault handling slices, CPU does something useful. However, in this giant idle slice, CPU does nothing but waiting for the SSD. So we could see that the slowdown mostly comes from cores being idle while waiting for the SSD. Right. But why this SSD is this slow? Let's take a deeper dive into that. And in this slide, we are going to see if we are getting the most out of our SSD. So in this plot, we are going to see a timeline of the SSD bandwidth utilization for our case study. These two green lines are the maximum bandwidth that our SSD can provide for read requests and write requests. However, this is the timeline for BFS web benchmark. We can clearly see that the average bandwidth utilization is less than 200 kilopages per second. In other words, our SSD bandwidth is underutilized by a factor of 4.6x. So our SSD bandwidth is underutilized and the SSD could do more work. But why is the SSD underutilized? Let's have a deeper look at it. Again, we have the same case study. And I should note that the SSDs are capable of handling requests in parallel if they are provided with enough requests in their queue. So in this graph, we are going to see the SSD bandwidth as a function of the number of in-flight requests in the queue, in the SSD queue, or in short, SSD queue depth. So our SSD can maximize its read bandwidth if it is provided with more than 128 page requests in its queue, or it can maximize its write bandwidth if it is provided with more than 16 requests in its queue. However, let's see where our case study is in this graph. So our case study, on average, can provide 3.4 requests in the SSD queue, and in turn, its bandwidth utilization is less than 200K pages per second. So the SSD is underutilized since its average queue depth is low, or in other words, there is not enough requests from our case study for the SSD. So the low average SSD queue depth results in poor SSD bandwidth utilization. Let's review the problem and its causes. So the problem we had was graph workloads do not fit into the main memory, and swapping as a commodity approach significantly hurts the performance because cores are idle and waiting for this swapping IO, and the SSD bandwidth is poorly utilized because there is a low SSD queue depth. Our solution for that is thread overcommitting. Thread overcommitting means dedicating more than one software thread per each physical core. If we do that, there is more work on other threads when a thread blocks for swap IO. Thread overcommitting keeps core busier, and it can lead to issuing more in-flight swap IO, and in turn, SSDs provide more swapping bandwidth. So busier cores leads to faster page fault generation, which in turn leads to more bandwidth utilization. And busier core, again, can hide some of the SSD access latency. Now let's see the overcommitting impact on SSD bandwidth and SSD queue depth. Again, we have the same case study, but before that, I need to introduce overcommitting factor, or in short, OCF, which is the number of software threads per core. In our experiment, we are going to vary it from 1 to 16. So we are already familiar with this graph. This is SSD bandwidth as a function of number of in-flight requests in the SSD queue, or SSD queue depth. Our case study was here in this graph because it could provide less than 4 requests on average in the SSD queue depth. However, if we overcommit threads, we can increase the SSD queue depth, and in turn, we can decrease the SSD bandwidth underutilization. So, in other words, we improve the bandwidth utilization by 2.5x for this particular case study, and we close the bandwidth gap for 40%. So more threads leads to more in-flight requests, which in turn leads to more bandwidth. Now let's have a look at the overcommitting impact on core's idle time. So for our case study, the idle time is about 50 seconds. If we overcommit, we can decrease the idle time to less than 20 seconds. And the CPU working time here is almost untouched. And the same happens for different percentages as well. So more threads leads to less CPU idling time. Now let's see the overcommitting impact on the performance. Again, we have the same case study, and we have seen this graph before. This graph shows the amount of slowdown if a part of our workload does not fit into the main memory. So for example, for BFS Web, if 70% of the workload does not fit into the main memory, we can get a slowdown of 8x. However, if we overcommit, the slowdown is decreased to almost 3x. We can interpret our results in a different way. So in this graph, we are going to see performance if some of the workload does not fit into the main memory. For example, for BFS Web, if 70% of the workload does not fit into the main memory, we can get a performance drop of 88%. However, if we overcommit, we can decrease the performance loss to only 67%. In other words, we reclaim 20% back from the performance. So our study included 6 different applications, 5 different input graphs, 8 memory capacities, 5 different overcommitting factors, which leaves us with 1,200 data points. And we gather many statistics per point. So we could not present all of them together. That's why we chose a case study to show in our slides. Now we are going to see the overcommitting impact on performance for different input graphs, as well as different applications. BFS Web was neither the best case nor worse. Most benchmarks gained performance, however, some lost. So for performance improvements, the maximum performance improvement was 4.18x with a geo mean of 1.65x. Let's conclude our work. The problem that we attacked was graph workloads do not fit into the main memory, and swapping is slow. Our contributions in this work was doing a characterization of system and SSD when executing graph applications, identifying why swapping hurts the performance, introducing a simple solution to overcome slow swapping, which led to up to 4.18x performance improvement with a geo mean of 1.65x. In our future work, we are going to answer this question: can we achieve more performance by exploiting multiple swap devices and increase the bandwidth? And we are going to explore hardware and software modifications to exploit more parallelism. Well, thanks for listening to us.